Hey everybody, how are we this week? Well, I hope. Just give it another minute or two for more people to join. So welcome to the 6 people who are already here. So tonight we're doing equilibrium, but it's with a year 12 slant. It's not the year 13 sort of take on it. I'll talk about the differences between year 12 and year 13 as we go through, but this is purely based on year 12 content. Okay, so I'll just skip the ads on my phone so I can see the comments. Live chat. Cricket Crazy, hi, how are you? I'm very, very well, thank you very much. Hope you are too. Okay. Right, okay, before we start the chemistry, I just want to point out a couple of things that you may not have realised. So, I don't know if you've noticed, but I've been uploading new videos pretty much every day now. So, I'm doing walkthroughs of exam questions. So that's kind of my new project, as well as the live streams, because I've pretty much covered everything else. So these are new style videos where I'm just picking one exam question and just going through how to answer it. But the way I've done the video is you can see the question on the slides, all blank. So you can pause the video, have a go at the questions, and then when you're ready for the answers, just play and I go through the answers. So you might want to check those out. I forgot to mention last week, but I'm sure you've seen, I've done all of the mechanisms. So I did a big half an hour, sort of 40-minute video on all the mechanisms. So I did 2 videos. I did the OCR ones, which was quite short. And then I did the Monster AQA mechanisms. So they're both on, so you could check those out if you wanted to revise your organic mechanisms. And obviously, I suppose it's a plug to get people to subscribe, because obviously if you are subscribed, you would get notified that I've done that, so you'd be kept in the loop. Okay. And obviously, you know, if you're revising other things other than what we're doing, I'm sure you are, check out my index doc, which is just the links to every single video that I've made. It's like a 30-page document now. It's a bit of a monster. But they're all on there. So if you were revising a particular topic, you can go straight to the doc and just find the videos on that topic and just play it and watch them if you wanted to. So the link to that doc is in the channel description on YouTube. I'm sure I've said this before, but if you're on Twitter, if you follow me on Twitter as well, it's my pinned tweet. Okay, so I can see there's quite a few more people on now, so hello to the new people who've joined. So we're looking at equilibrium this evening, and it's a year 12 take on equilibrium, because the assumption is most people here are year 12 students. So I don't want to confuse you by bringing in stuff that's going to be taught to you next year anyway. And on Friday at 3 we'll be doing the questions that I've already set. So we'll do the iPad type of lesson, because that seemed to work pretty well last week, I think, hope anyway. I'm sure you said it. You said it was good for that, so we'll continue with that. Right, okay then. So let us begin. I've noticed loads of messages flying up, and so I'm just going to check any sort of quick questions apart from all the hellos. Sorry, I haven't got time to say hello to everybody that said hi, but hi everybody. Okay, it's great that you're here. Is there a specific exam board that I cover? Well, I teach OCRA, so obviously my videos are geared towards that syllabus, but I know for a fact from people, other teachers follow me on Twitter and they point their students to my videos, and they teach AQA, or they teach EdXL, or they teach lots and lots of other exam boards. So it shouldn't really matter which exam board you do. The bulk of the chemistry on all of the UK exam boards is the same. So there's just tiny little differences 5%. I think it's about, there's 5-6% difference in the syllabus, and apart from that, it's fairly constant. Okay. Oh, excellent. So well done on your mock exams. That's really good. Really, really good. I'd like to think I was of some help for you, so that would be good. What's the difference between OCR-A and OCR-B? I've never taught OCR-B, but I know it's sort of, it's all set in kind of chemistry set in contexts rather than a sort of traditional approach. OCR-A is more traditional, so this is the content, this is the theory, so you kind of go and learn that and understand that, and then they ask you questions directly linked to that. Whereas OCR-B, it's kind of, you still learn the content, but the questions are set in a sort of scenario, like a story kind of thing, and you've got to unpick from the story what the chemistry is, and then apply your chemistry knowledge to that. So it's a very, very different approach. Personally, I wouldn't really feel comfortable teaching that. I know some teachers love teaching it. I've never taught it. That's probably why I probably wouldn't want to do it now. But anyway, that's the difference. Am I doing calculation of moles at equilibrium from Casey? No, not tonight, because that would be year 13 stuff, okay? So I imagine you're talking about the ICE method, so initial moles, change in moles, equilibrium moles. I've made loads and loads of videos on that stuff. Very, very popular as well, if I don't sound too big-headed. So you could check those out, and you could watch me on YouTube, but on these particular videos. Go to the index doc that I mentioned before, and they're all there. Okay, and the links are there. You can just go straight to them. Right. Okay. So I think that's all the questions. So let's make a start then. Okay. So the first thing I've got on the board there is just to sort of set the scene, establish the difference between a reaction like this and a reaction like this. Okay. So the first one is obviously magnesium and and sulfuric acid. So you've probably done that at college or school. You drop the magnesium into the test tube of sulfuric acid, and it fizzes. The magnesium dissolves away, turns into magnesium sulfate, and the fisson's obviously hydrogen. When that reaction, sort of the fission stops, the reaction's over, and basically what that reaction is it's an irreversible reaction. So it can't be reversed. You can't take the hydrogen and magnesium sulfate and send the reaction backwards, okay? So this is an irreversible reaction. Okay, so it's a one-way reaction. However, if you took some sulfur dioxide and oxygen, the important thing here is they need to be in a sealed container, okay, also known as a closed system. Okay, so if you place those two gases in that container, they would react and form sulfur trioxide. However, the sulfur trioxide would actually break apart and reform sulfur dioxide and oxygen. So this is an example of a reversible reaction. Okay, so that's kind of the starting point for this topic. So we've got reactions that are irreversible and we have reactions that are reversible. Okay, so when can you say that it's in equilibrium? So that's, you've got to get your head around what we mean by reversible, and then what do we mean by equilibrium, okay? So remember, we're in this closed system, so that could just be a sealed flask or something like that. And when you have two conditions met, you have what's called a dynamic equilibrium. I'll explain dynamic in a second. Okay, so the first thing is when the rate of the forwards reaction, so this reaction here, so when the forwards rate equals the rate of the reverse reaction. Okay, hope you can make sense of that. So when the forward reaction rate equals the reverse reaction rate, what's going to happen at that point as well is the concentrations, I'll just put concs if that's okay, the concs of all species, so sulfur dioxide, oxygen, sulfur trioxide, remain constant or don't change. What we can say at that particular point, that's what we call a dynamic equilibrium. Okay, so it's got to be in a closed system. The rate of the forward reaction has to equal the rate of the reverse reaction, and the concentrations of everything remains constant. And hopefully you can see why that would be the case, because if the sulfur dioxide and oxygen are breaking down as quickly as the sulfur trioxide is breaking down, then their concentrations will effectively remain constant. They're not going to change. Okay. Now, the analogy I always use, just to get it into students' heads, is if you think of a treadmill. So I'm sure you've seen a treadmill, you've probably already been on a treadmill in a gym, if you're a member of a gym. So a treadmill is a dynamic equilibrium, okay? So when the person running is running at the same speed or rate as the belt's going in the opposite direction to the runner, that's a dynamic equilibrium, because the dynamic bit is things are still moving, okay? So this reaction never ever stops, it's always moving, okay, like the treadmill and the runner. But if you think about a treadmill, when the runner is running at the same rate as the belt, it's like they're running on the spot. They're not running forwards, or they're not running backwards, they're actually running on the spot, okay? So I think that's quite a useful analogy, just to sort of get the idea in your head that this reaction's constantly on the go. Okay, you've always got everything present, and that's what we call a dynamic equilibrium. Okay, so I'll just pause for a second and see if there are any questions at that point, because then we're going to move into Le Chatelier's principle next. Okay. Okay. Right. Okay, Chatelier's principle. Okay, so Le Chatelier's principle, it's quite a wordy definition. So when you've got a system in, I'm just going to put DE, dynamic equilibrium. So when a system in dynamic equilibrium is subjected to an external change, the system will shift, or you could say respond, to minimize the change. So just going back to that treadmill analogy, if you've got the runner on the belt and everything's in dynamic equilibrium, and then somebody slyly presses the sort of speed up button on the belt, the person running has to speed up as well, otherwise they would no longer be in equilibrium and there'd be in a bit of a problem. So it's a bit like that, you could think of it like that. Okay, so what I'm going to do is I'm going to use the same equilibrium for each of the factors, okay? Rather than change, and then I've got an industrial example to show you at the end, so we can sort of see a different equilibrium, if that's okay. And then the questions that we're doing on Friday, they deal with lots and lots of different equilibria, so you'll see plenty, I'm sure, over the course of this week. So the example I'm using is the one I've already shown you, so that's 2 SO2 gas plus O2 gas in equilibrium with 2 SO3 gas, okay? And I'm going to add this, I'm going to use in one of the factors, I'm going to tell you that the delta H, the enthalpy change for the forward reaction, is negative 196. That's obviously kilojoules per mole, okay? Just before we move into this, so when we say shift, okay, what I mean by that is it can either move more to the right, or you could say forwards, or more to the left, or backwards. Sorry, a news flash has just come up on my phone. I'll just put the get the notifications off. Sorry about that. There you go. Do you have to say the equilibrium would shift? You would say shift, move, respond, anything like that, okay? Which word were you thinking? You can pop it in the comments and I'll check for you, but I'm sure as long as you're kind of getting across that, that sort of concept, you'd be fine, okay? Right, so I'll just change colour so it stands out a little bit. So the first thing we'll look at is the effective concentration. Now, if there's any Year 13 students in the room, you'll be familiar with explaining an equilibrium shift in terms of the equilibrium constant, Kc. Kc is just kind of mentioned a little bit in Year 12. So what you tend to have to do is, in Year 12, you would mention it in terms of Le Chatelier's principle. So all the stuff we're going to talk about now is in terms of Le Chatelier's principle. In Year 13, the questions would then probably start saying, explain the equilibrium shift in terms of the equilibrium constant. So I'm not really going to go down that road tonight. I've said that a few times now. Okay, so this is purely looking at Le Chatelier's principle, which you could still be asked at the end of your second year. Okay, so they could pick and choose which way they want you to explain it. So this is Le Chatelier's principle. Right, okay, so let's imagine that you increase the concentration of one of your reactants, okay? So let's just pick sulfur dioxide because I'm right next to it here on the board, okay? So if that was increased, obviously that's going to knock it out of equilibrium, okay? So how does the equilibrium respond to bring this back down? Well, if the forward reaction happens a bit more, then that's going to bring the sulfur dioxide concentration back down, and so it's going to re-establish its equilibrium, okay? So if you increase the concentration of any of your reactants, the equilibrium would move more in the forwards direction, okay? Or you could say more to the right to re-establish the equilibrium, okay? If you increase the concentration of the sulfur trioxide, obviously that's made that go up, so it needs to come back down again. So the reverse reaction would bring the concentration back down and send the equilibrium, so the equilibrium would go to the left or backwards, more backwards, until the equilibrium is re-established. And then there's a couple of other ways we could say this. So let's do the opposite now. So let's imagine you lower the concentration of one of these. So if this comes down, it needs to go back up again. Well, how does it go back up? This reaction, if this happens more, it's going to make these go up a little bit, back to equilibrium. Likewise, if this goes down, this goes down. If it goes more forwards, it'll go back up again. Okay, so trying to put that into very sort of concise wording is quite difficult. We'll give it a go. I'm sure you can sort of work this out. So let's just use one of the examples. So if concentration of any reactant is increased, the equilibrium will shift to the right until equilibrium is restored. And then I'm just going to put etc., etc. for all of those other scenarios that were mentioned. Okay, so I'm just going to see if there's any comments on that one. Right, okay, what's that saying? I meant, would you state that the system will shift or the equilibrium will shift? Well, the system is the it's it's just sort of the terminology that you use. So system or equilibrium would be fine there, okay? Was that okay with the effective concentration? Does anybody want to ask me any questions about that before I rub it off the board? When you get into year 13, you will see, no problem, you will see another way of explaining that in terms of the equilibrium constant. And I'm sort of itching to tell you now, but I shouldn't really until you get into year 13, okay? If you desperately want to know, you could just check out my video on the KC stuff, and that would tell you anyway. Okay, right. It's fairly straightforward, that one, so I'm not surprised there aren't any questions there. Right, so let's do the next, excuse me, the next factor, which is temperature. Okay, so if you are trying to establish the effective temperature, what effect that's going to have on an equilibrium position, so which way will it shift, then you've got to look at the sign of the enthalpy change. That's where you need to look, okay? So I'm going to write on there straight away, look at sign of delta H. If you're making notes on this, that's the most important thing you need to do. So temperature, look at the sign of the delta H, okay? So you can see there that this forward reaction has got a negative enthalpy change sign. So that means the forward reaction is exothermic, okay? So what we're going to do, so look at the sign of the delta H, and then what you do is you establish the exothermic and endothermic reactions. Remember, there are two reactions. If one of them's exothermic, the other one must be endothermic, okay? So we've just established from that minus sign that this forward reaction is exothermic. So I always tell my students, write exo on above the forwards arrow and write endo underneath that reverse arrow, okay? If that's the way it is. Obviously, if that was positive, they would be the other way around, wouldn't they? Okay? Right, so if we think about it, this is how I was taught to think about it, and then the teacher would say, well, don't write this, okay, but think about it like this because it helps. So if you've got this at equilibrium and you heat it up, it wants to get back to the temperature it was at equilibrium. I nearly said happy there, so I shouldn't say that. So it needs to get back to the temperature that it was at equilibrium on. So if you heat something up, which reaction is going to absorb that heat and take it away? Well, it's the endothermic reaction, which is the reverse reaction for this equilibrium. Okay? So the thing to remember is an increase in temperature will always favour the endothermic direction. Increase in temperature favours the endothermic direction. Okay? So increase in temp favours the endothermic direction. Okay? And obviously, likewise, if you cooled it down, it wants to heat back up again. So which reaction gives out heat and makes it sort of hotter again? Well, it's the exothermic reaction, which in this case is the forwards reaction. So a decrease in temperature favours the exothermic direction. Okay, so if you remember those two sort of key statements, as long as you know which way is which, you can't get these wrong. Okay, so just seeing some questions pop up, so I'll just have a quick look and see what these are. Yeah, so why does the equilibrium need to... Right, Maya, I'm afraid the explanation to that is locked in the year 13 content. Okay, I'm not ducking it, but I just think it might confuse people if I start going into the sort of real kind of getting to the bottom of KC. It's all about the equilibrium constant. Okay, which I haven't mentioned yet in this lesson. But every equilibrium has what's called an equilibrium constant, and depending on what factors changed, different things happen, and you need to learn all the different sort of scenarios possible for that. But like I said, check out, I've got it all explained on other videos if you wanted to have a look at that, if you desperately wanted to know. But in the meantime, just if you're happy to accept that it sort of moves to oppose the change. So if you heat it up, it wants to cool back down again. Okay, it does that by following the endothermic direction. It's a bit more, it is more complicated than that. But for AS level, which is what we're doing, that's what you would say. Okay, right, thank you. I hate doing that. I feel a bit rubbish because I feel like, you know, students genuinely want to know, but you're talking quite a while to explain that, which we haven't got. Okay, and not everybody might be interested, so there you go. Right, so is that okay for temperature? Year 12 chem. It's not difficult, man. It's fine, it's fine. Right, so the next factor we're looking at is pressure. Okay, now pressure is only going to affect gaseous equilibria, which is what we've got here. This is why I've deliberately chosen that. We don't need the exo and endo stuff anymore, so I'll get rid of that. Okay, so where do we look if we want to know how the pressure is going to affect the equilibrium? We don't need to look at the enthalpy change sign, that's irrelevant now. It's all to do with how many moles of gas you've got on the left versus the right. So that's the first thing you should look at. So let's just write that in, just see how I'll phrase it on here. Yeah. So the first thing you do is look at the moles on each side. Okay, so what I always tell my students to do is, like we wrote exo and endo on there, how many moles have we got on the left? We've got 2 plus 1, so we've got 3 moles of gas on the left hand side. How many have we got on the right? 2. So get that written onto your, if you're answering questions, get it written onto the equilibrium straight away. So write exo there, so and then write exo, endo, write 3 moles, 2 moles in this case. Just put it all on straight away. It takes you a matter of seconds to do that. But then once you start looking at the question, you've got all the clues there, you've already processed it, it's dead easy to come up with the answer. Okay, so look at the moles on each side, right? And again, if anybody's possibly queuing up with, but why does it really do that? Well, it's all to do with KC, and it's quite it can be quite complicated. All right. So the thing we need to remember is if you increase the pressure, okay, so an increase in pressure will favour side with the fewest moles. Now, when I was taught this back in the 80s, my chemistry teacher said, imagine James Bond's in this room and the walls are collapsing in. How would he, so the pressure's increasing on him. There's no way he can fight against those, these things coming in. He knows that someone's going to switch it off. So how do you minimize the effect of that pressure on you? You curl up and make yourself as small as possible. That was his way of explaining it to us. And then he obviously would say, but this is how you're going to have to explain it in the exam. Okay? So an increase in pressure will favour the side with the fewest moles. So in this example here, an increase in pressure will push this equilibrium over to the right hand side. Okay? So this is useful for industrial processes. If you want to maximise your yield, then you can use pressure to sort of push the equilibrium, and temperature as well, obviously, to push the equilibrium forwards, okay, and make more product. Okay, so increased pressure will favour the side with the fewest moles, and obviously the reverse, the flip side of that is true as well. So decrease the pressure will favour side with the most moles. And if you desperately want to know more about that, it's all locked into the KC stuff. Check out my videos on that if you want, and I'll explain it to you via that method if you wanted to get a head start for next year. Okay. Any questions on this? I'm just going to do one more example under here, and then we'll finish off with catalysts. So I just thought I'd include this one, just so you've got a sort of slightly different example. So if you had something like this one, suppose you had hydrogen and say iodine in the gaseous state, in equilibrium with 2 moles of HI. We're interested in the pressure effect, so we don't need to know the delta H value. What's pressure going to do to this equilibrium? Well, look, we've got 2 moles on the left. We've got 2 moles on the right. So there's no big side and small side. So pressure won't change this equilibrium. It won't be affected. The position of it won't be affected by the change in pressure. Obviously, an increase in pressure would increase the rate of the reaction, because the collisions will be happening more frequently because you've pushed everything closer together, but it won't make the equilibrium go more forwards or more in reverse. Okay, so I just thought I'd show you that one as well. Okay. Yeah, so there's there's 2 moles of molecules. So there's 3 moles of molecules there, so there will be 3 times Avogadro's number of molecules, and there's 2 moles of molecules on that side. Okay. Yes, I am going to mention the simple case C stuff tonight, but I'm not going to go into the complicated stuff. I'll leave that for year 13. Right. So the final thing is the effect of a catalyst. Out in time, 36. So the thing we need to say is the rates of both reactions. Remember, we've got 2 reactions. We've got a forward reaction and a reverse reaction. Rates of both reactions affected by the same amount. So catalysts do not alter the equilibrium position. Okay, because the forward reaction is sped up as quickly as the reverse reaction, and so the overall effect of that is no change in position. So it wouldn't go more forwards or more backwards. Obviously the time taken to get to equilibrium would go down, but it's not changing the position of the equilibrium. I'll put that on. Time to reach equilibrium would be less with the catalyst. Okay. Okay. So that's Le Chatelier's principle. So before we go into the KC stuff that I am going to do, I just thought we'd look at a classic kind of question that would be asked. I've got this question from quite a recent OCR paper. Okay. Yeah, that's right. So the catalyst gives an alternative pathway for the reaction with lower activation energy, so more of the collisions are successful. So you've got more frequent collisions with energy greater than or equal to the activation energy, but that's the case for both reactions, and so their rates are equally sped up equally, and so there's no overall effect on position. Okay. Right, so get rid of all of this. Right, I've literally just decided to not use the one in my notes, and that's because I've made a video on it. So if you wanted more practice at these, you could check out the video that I've literally just made a few days ago. So I think it's called, they've all got the same kind of cover now. It's called Exam Question Walkthrough, and this one's the equilibrium, sort of equilibrium and equilibrium constant, I think it's called. So it might be worth checking that out. So I'm going to use a different one. I'll use the classic Harvard process one. So that's nitrogen, N2 gas, 3 moles of hydrogen gas. I'll bet you're sick of this one. 2 moles of NH3 gas. And the delta H, I know this off by heart, is minus 92 kilojoules per mole. Okay, so a very common question that they will ask is suggest the conditions, using Le Chatelier's principle to explain, suggest the conditions for the maximum yield of ammonia. So in other words, what's going to send this equilibrium as far over to the right as possible to give the most ammonia, big yield. And then the next part of the question is, suggest why these conditions aren't used in industry, okay? So suggest why they're not actually used. So if you want to have a think about that, it's getting a bit dark in here, so we'll see if this makes any difference. A little bit. Then I'll give you, 2 minutes to think about that, and then we'll go through the answers. I'm sure you've answered stuff like this before. Let's get out the shot. So they don't expect you to know the actual temperatures and pressures. They just want to give a flavour of whether it's high or low, that sort of thing. That's all I'm going to talk about. I'm just looking at your question there, Crazy. I would say you need to say that it's in an orbital, because the electrons are paired up in orbitals. The subshell is the collection of the orbitals of the same type of orbital. So I would say that you need to say orbitals there. Jake, just have a look at what you've typed, because just have another look. Right, okay. It's easily done, isn't it? That's so easy to do that. Right, okay, let's go through this. So what we're doing now is what are the conditions that Le Chatelier's would suggest would be the best conditions to use, and why. Okay, so in terms of temperature, remember what we said, the first thing you look at is that sign, it's negative. So I would say forward reaction, get that in first. I'm just going to put Rx in, it's exothermic, therefore a low temperature would be preferable, okay, for the yield. Okay, so forward reaction is exothermic, therefore low temperature is going to favour the forwards reaction, exothermic. In terms of pressure, we're looking at the moles, so we've got, or we're not looking at the number of molecules or the moles of molecules, 1 plus 3, so there's 4 moles of gas on the left hand side versus 2 moles of gas on the right hand side. So that's the smaller side. So you could say that the products side has fewest moles. You could quantify it if you wanted to. You've already quantified it if you put it up there, so I wouldn't worry about that. Therefore, high pressure. That's literally all you would need to say, okay? Right, so are they likely to use these conditions? And if not, what would they do? Okay, so we'll deal with the temperature first. Low temperature, what can we say about that? The rate would be too low. Okay, so yeah, in theory we should get lots of ammonia, but it would take ages to get there. So they can't wait for that to happen. So what they're going to have to do is increase the temperature. Okay, now obviously that's going to have a negative effect on the yield, because it's going to favour the endothermic reaction. Remember, this one's exothermic, this reverse reaction's endothermic. So they're not going to want to heat it up too much, otherwise they'll be favouring the reverse reaction too much. And also there's all those energy costs from the extra heat energy, the fuel it needs to generate the temperature. So it's what they call a compromise between rate and yield. So low temperature, rate too low, so would use higher temperature. Okay, the pressure, so the high pressure. So I tend to tell my students, don't sort of go down the it's too expensive kind of thing, but you could mention it. High pressures are very expensive to generate, and what you could say is they're very difficult to sort of maintain. The process becomes very, very problematic at high pressure, because if you think about the pipes, the joins in the pipes, high pressure is going to burst the pipes quite easily, so the maintenance costs are going to be quite high, and also it's a risk. The higher the pressure, the more dangerous the process would be. Okay, so high pressure, so you could say expensive to generate and maintain, also higher safety risks. So what they would probably do is bring the pressure down a little bit, and obviously that's going to have a negative effect on the yield, because a lower pressure is going to start favouring the side with the most moles. So it's this compromise word that's used between the yield and the rate. Okay, so that's it. I'm sure you've done loads of questions like that before. Okay, right, let's just check the chat and then I'll go into case C. Yeah, cat, compromise. Yeah, was that okay? Was my sort of ramblings on about compromise okay for everybody? Okay, just give it a second. All good, all good. I've gone quiet. Right, I'll take that. I'll take that as it's fine. Oh, something there. Right. Like I said earlier, when we do this questions on Friday, I'll go through like how to answer, the sort of wording I would suggest use. Tonight, the purpose of tonight is just to get the theory side of things refreshed in your minds, and any little things you didn't quite understand the first time round, hopefully you do now. Okay. Right, so the equilibrium constant. So that's Kc. Okay. So the first thing is, well, what does Kc tell us? It gives a measure of the equilibrium position. So is it more to the right or is it more to the left? Is it more forwards or more backwards? So the size of this Kc value is a measure of how far the equilibrium is forwards, or is it more backwards? And you'll see how that's measured in a second. Okay, so if we just think about any equilibrium, can be simplified to this: reactants in equilibrium with products. Okay, so all Kc is telling us is it's a ratio between the concentrations at equilibrium of the products to reactants. So Kc, and we use square brackets for concentrations. I'll put a key down there in a second. So it's products on the top over reactants. So this is obviously the simplest type of Kc expression. So just explain there that the square brackets refers to the equilibrium concentrations, and they're obviously measured in moles per decimeter cubed. Okay, now somebody earlier on asked me, am I going to go through the mole side of KC? And that makes the questions quite a bit trickier. So that tends to be what we do in year 13. So we just kind of establish the basics of KC in year 12 and then go into the sort of more complex stuff in year 13, where all the sort of maths kicks in. Okay, so these square brackets refer to equilibrium concentrations in moles per decimeter cubed. Right, so let's suppose if the equilibrium, I'm just going to put EQM if that's okay, if the equilibrium is well to the right hand side, okay, so if equilibrium is well over to the right hand side, just think about how these concentrations would compare with each other. So if it's well over to the right, you're going to have a higher proportion of product concentration to reactants concentration. So if you just think about it like a fraction, you're going to have a bigger number on the top compared to the bottom. Okay, so that's going to give you a Kc value greater than 1. Okay, and obviously the bigger than 1, as it gets bigger and bigger and bigger, it means the products are far outweighing the concentrations of the reactants at equilibrium. So the equilibrium must be really over to the right hand side. Okay, so sometimes they would use this double greater than arrow. If it was really bigger than 1, that means it's well over to the right hand side. That was actually asked a couple of years ago. They used that double greater than sign. Okay, so if let's just do the flip side of that. If the equilibrium is well to the left hand side, hope Jake's alright, using lefts and rights now, so sorry I couldn't do this. If the equilibrium is well to the left hand side, that means it's more this way. The reactants concentration is going to be way higher than the products concentration. So think of it as a fraction, that's the bigger number now. So Kc is going to be less than 1, okay? Kc is less than 1. And imagine if Kc was kind of in the middle, or if the equilibrium was in the middle, sorry. If the equilibrium was in the middle, so these are kind of roughly the same, Kc would equal 1. Okay, so a couple of questions ping up there. So yeah, so Kc, the little c stands for equilibrium concentration. Okay, so that little c there stands for concentration, obviously in moles per decimeters cubed. There is such a thing as Kp, so it's just another equilibrium constant that we use. There's lots of equilibrium constants, by the way. There's Ka, there's pKa, there's Kb, there's pKb. Most of those you'll come across in second year. There's Kw, another equilibrium constant. That's for water. So in year 12 we only talk about Kc, but if you're dealing with gaseous equilibria, you can use something called Kp, which deals with things called partial pressures. So the individual pressure of each gas component in the mixture can be used to calculate the equilibrium constant. Okay, so you would call that Kp instead. So you might have seen it somewhere, but we don't use it in first year chemistry. Okay, any questions on this? Don't think so. So I'll keep that on the board. Right, so we're nearly at the end now, you'll be pleased to hear. So the next thing is we need to be able to writing expressions for Kc. So let's go for the equilibrium that we used all the time in the Le Chatelier's principle stuff. So that was 2 moles of SO2 plus O2 in equilibrium with 2 moles of SO3. Okay, so remember, that's the basics. We need the product concentration on the top, so this is going to be on the top, and the reactant concentration, these things are going to be on the bottom of the expression. The thing to note is that the coefficients, so what I mean by that is the balancing numbers, the coefficients become powers. Okay, so coefficients, the numbers we use to balance the equations with, they turn into powers in the expression. So what would the Kc expression look like for this? So product on the top, square brackets for equilibrium concentration in moles per decimeter cubed, SO3, coefficient of 2, so it becomes squared. Okay, divided by the equilibrium concentrations of the reactants. So we've got 2 reactants, we've got SO2, so that's a square bracket, coefficient of 2, so it's squared, and it's not plus, it's multiplied by. Okay, so you can either put a multiplication sign in, you can put a dot in, or you can just leave it without and just have the square brackets next to each other. That's absolutely fine as well, but I've put the times sign in, so I'll keep it there. O2. So you can see that's been balanced with no number needed, so obviously there's a 1 in front of it, an invisible 1. You don't need to write power 1 there, okay? So I wouldn't bother personally, I'll just leave it like that, okay? So common mistakes I see, I think the most common mistake I see is students would put a plus sign there. That's the most common mistake I see when I'm marking work. And it's probably because they can see one in the equation, so they just mirror it in there. And they've obviously forgotten, because obviously I've never told them to put a plus sign in there. Always said multiplication, okay? So that would be the equilibrium constant for that one there, okay? I'm confused with this comment here. It's probably way up in the chain, so I'll have a look later on. I don't think, all right. Oh, haha, thank you. Right, it's obviously nothing too major. Okay. Do you want to do another one of these, or are you happy with that? It's fairly simple system, so product over reactants, the coefficients become powers. I've got another one here, but it's in that video, so it's fine. Right, good. Okay. Right, so basically we're nearly there. I'll probably get the rest of the stuff here. So for year 12, what you need to be able to do, so you need to be able to calculate, okay, what's the matter with me? Kc from given equilibrium concentrations. So at year 12 level, you will be told what the equilibrium concentrations are. So all you have to do is establish the Kc expression, put the numbers in, remember about the power business, and don't put a plus between terms, it's always multiplied, and you've got to be able to calculate Kc, okay? you might be asked to say, what does this tell you about the equilibrium position? So if Kc is greater than 1, you'd say that it's further to the right. If Kc is less than 1, you'd say it's further to the left. They're the kind of questions that they would throw at you at this stage. In year 13, I don't want to scare you, but in year 13, they don't give you the equilibrium concentrations. They give you the starting moles, and you're given a bit of information where you've got to work out what the equilibrium concentrations are. And that's where I use a method called the ICE method. So initial moles, change in moles, equilibrium moles. It's like a 3-step calculation. Obviously, that's too complicated for tonight, no offense, okay? But if you wanted to check out my stuff on it, feel free. The other thing they might ask you to do is they might give you Kc. So they could give you Kc, and they could give you, say, if it was this one, for example, they could give you Kc and let's say those two equilibrium concentrations, and you would have to solve and find out the equilibrium concentration of the sulfur trioxide, okay? So as long as you know everything else apart from the one that you're looking for, you can rearrange, so your math skills kind of kick in there. The chemistry is quite basic, it's more maths related problem solving than chemistry, okay? So, what have I got written in my notes here? Yeah, I've just said here, yeah, if you're keen on knowing the year 13 stuff, or if you are year 13 and you want to see more complicated Kc calculations, just check out my videos on it, and I'm sure you'll find stuff there, okay? And in year 13, like I said before, we explain equilibrium shifts a different way to we have tonight. So instead of Le Chatelier's principle, we use the equilibrium constant Kc. Right, what time is it? 8:02. All right, that's not too bad. Okie doke then. So I am going to go in a second. So yeah, right. Thank you, Cricket Crazy. Yeah, you always make me feel good. So that's really nice of you. Thank you. What was I going to say? Throw me off track there with that. Yeah, check out the videos that I'm making. Okay, so I've already made 2 more. So I've got one to post tomorrow, another one to post on Friday morning. You know, hopefully you'll find them interesting. Give them a watch. Obviously, it's good for me. It gets keeps the channel kind of ticking over, which is brilliant. And yeah, that's it. Hopefully see you on Friday, and we'll have a think about what we're going to do next week. Okay. Let's see, lots of comments. Friday, when we're going through the questions, Friday at 3 p.m. So, am I making any AQA videos? Is there anything specific you would like? And I will look at that. Obviously, what I've got to do is check out the AQA specification and sort of make things accordingly. You're welcome, Maya, if you're still there. Just waiting for Laura Ladybird to say which topic she was thinking. Mass spectrometry process and calculations. Okay, so are you talking about how we use mass spec to calculate atomic masses, relative atomic masses? Massive delay on this line. I hate all this silence. It must be terrible for you guys. Who's still on? Oh, there's 18 of you still there. It's very good of you. I have made some mass spec. Videos. Oh, right. Okay. Using the kinetic energy equation, speed, distance, and time. Okay. So yeah. Mass spec at AQA is very, very different in terms of the things you need to know compared to OCR. So my videos, possibly too simplistic for AQA. I think the calculations for calculating atomic masses will be the same. Time of flight, yeah. I'll tell you what, I'll have a look, and when I get time, I will make you a video on that, okay? So, not sure when it'll be, but I will make a video on, yeah, time of flight mass spec, yeah, okay. Because what I'll need to do is, I don't want to put anything on YouTube, certainly don't want to put anything on YouTube that's wrong, or I don't want to get it wrong, or I don't want to say it badly. And because I don't teach AQA, I'll need to just check that I've got my understanding of it correct, before I go on YouTube and get absolutely slaughtered by people for saying you've explained that wrong and all that sort of thing. So I'll look like a right idiot if I do that. So, okay. Do I teach OCT board? I'm sorry, I've never heard of the OCT board. Yeah, physics and maths tutor as well. Well, Maya, I haven't decided yet. So if you want to pick a topic, you could do that. Oh, do you know? I don't know. I don't want to say this now, but we could possibly make it time of flight mass spectrometry. But we'll see what people want. I'm sure Laura would want that, but maybe not everybody would. Any other people wanting to say what topics they want next week? Group 2 metals. I did a lesson this morning on Group 2 metals, the AQA Group 2. Alcohols. I did alcohols, didn't I? I did that last week. Can I do some past paper walkthroughs? I'm making a past paper walkthrough video every day. There's new ones going on every single day. So just watch them. Yeah, I teach OCR. Identifying ions tests. Oh, that's a good shout. That. So qualitative analysis. Yeah, I teach OCR. Yeah. Can I do Excel videos? I'd need to check out the syllabus and see how different it is to what I already do, okay? If I've got to do them completely from scratch, it's going to take a long time. If I can use stuff I've already made and just tweak it slightly, then I could probably churn out some Excel videos very, very quickly, to be honest. Yeah, it's fairly similar. So, would you not just use the ones I've already made? Beginner year 12. Do you know what? I'm gonna get a T-shirt printed with answers to all these questions on, because I keep getting asked the same questions every week. So I'm gonna get a T-shirt that says I teach OCRA. Edexcel and AQA are very similar to OCRA. I hope I'm not offending you by saying this. What else could I say? Please check out my video index for all the other videos I've made if you're stuck on a topic. What else could I say? The link to my video index is in the description to... I'm being cheeky now, sorry, I'll stop. Still 17 people on roasted. Who, me or... Yeah, that's pretty bad. That yeah, but I better not say anything on that front. But yeah, That would be a great t-shirt. I think you're taking the mic now, aren't you? Okay. Right. You would probably buy that. I know somebody who makes t-shirts as well. I might put an order in for a laugh. I don't know how much it would cost. Like, I've already got a t-shirt and a cap, a baseball cap with mountain guy. Oh, and a plectrum because I play the guitar. Somebody got us a plectrum made, so I have got merch. But yeah, okay. Still 16 people, and have you not got? Do you not want to go? You can stay if you want, but is there a store? Ha ha. Yeah, I should sell it, shouldn't I? At least I'll be able to sell 3 things to somebody. You've got nowhere to be, so you just stay in. Okay, fair enough. Fair enough. So, how's the weather where everybody is? Shall we chat it up? There's 19 people on now. People are joining. God. How's the weather? It's pretty horrible here. This is too entertaining to leave. Oh, great. I'll just show you the weather outside. The weather is cold, yeah. You can see the rain on, that's our street. Where is here? I live in a place called Sunderland, which is in the northeast of England. So it's quite close to Newcastle. So it's about 10 miles from Newcastle. It's about 10 miles from Durham as well. So I'm sure you've heard of those 2 places. But yeah, Sunderland's on the coast. Newcastle's a bit more inland and Durham's inland as well. So yeah, that's where I live. The weather's normally rubbish here, but it's been quite nice the last few days until today, but that's why I'm wearing this. I've been freezing today. So there. I can't believe I'm chatting away to 18 random people on YouTube. Yeah. Okay. Right, it's all gone quiet, so I think it's possibly, is that a sign? English weather is deceiving. Oh, right, sad. You might be applying to Newcastle. That's where I went a long time ago. It's a great university, so I would recommend it. And Newcastle's a fantastic city. When I was at Newcastle, I basically, even though my home was here in Sunderland, 10 miles away, I lived in Newcastle for 4 years, so I didn't really come home very much. But the great thing was I was only 10 miles away if I needed to do any washing, so that was pretty good. So what did I study? I studied chemistry, surprise, surprise. I did a degree in chemistry, just pure chemistry. Didn't do any sort of, it's raining, Laura. Where are you? I think it's raining everywhere, to be honest. So miserable for Jake. Okay. Hopefully I'll get out on my bike tomorrow morning. That's the plan. Do I have a master's? I just did a bachelor's I did a bachelor on an honours degree in chemistry. And then I did a PGCE, so I did a sort of teaching qualification, postgraduate in education. So that was that. I could have done a master's, but I needed to start earning some money basically, so that's what I did. Okay. 18 people still here. Bizarre. This is bizarre. Any other questions? No, it's all gone quiet. Okay, right. I'm gonna go. All right. So, yeah, I do. That's the polite thing to do, isn't it? I can't just leave and while there's people still here. You're off now. Bye. Okay. I think I'll just go as well. I'll take a leaf out of your book and just go. See you later. Bye.